Okay, we see your screen, so you can start.
I need to unmute myself also. Okay. So, yeah, I'll just start right away, right?
Yes, you can start, yes.
Okay. So, yeah, thanks for having me. Thanks for organizing this nice meeting. Yeah, in this talk, I'm going to discuss from a machine learning perspective, I'm going to discuss a supervised regression task, namely quantum measurement as a supervised regression task. And the specific system that we are dealing with is ultracold atoms and their measurement in so-called single-shot images. And usually, okay, when you have such a system, you want to extract some distributions of observables from your measurements. And this extraction we are considering as a supervised regression task and apply machine learning tools to it. In this talk, we put to the field two open source software packages, namely the multi-configurational time-dependent hard-free for indistinguishable particles to simulate the ultracold atomic systems and their detection, and Unicorn, the universal neural network interface for quantum observable readout from n-body wave functions to do the supervised regression task that I just discussed. Before I start, let me give you an outline. I will briefly introduce the system, ultracold atoms, and what single-shot images look like. I will run you through the background, how we theoretically describe them, give the Hamiltonian and the data set that we generate, and then introduce the machine learning algorithms that we apply to the single-shot images. I'll show you some example results and conclude. And as the first part of my introduction, let me do some shameless self-advertisement. There is a nice journal club that we created where everyone is welcome to present their most recent results on quantum physics and machine learning. So you have the slides, you can click this link. If you're interested, get in touch with us. All listeners and contributors are welcome. So let's get to single-shot images. This is an interesting image, although it just shows one dot. This is a barium atom, and it demonstrates this image that actually single-shot images, observations of ultracold atoms, go down to single atom resolution. Okay. I have another one which is sort of maybe more realistic for the Bose-Einstein condensates that we are going to consider later, where you have a huge blob with tens of thousands, probably hundreds of thousands of ultracold atoms in one image. And because I like these pictures so much, I put some fireworks that the Chin group generated by modulating the interparticle interactions of the atoms. So these are really like bursts of atoms flying away from a center. Sort of this shows that, okay, ultracold atoms are a really uniquely flexible tool to achieve many different physical states with quantum systems, and they're worthwhile to investigate in more detail. And it's worthwhile to look for what type of gains we can get by applying machine learning to looking at these images. Okay, and this is the scope of the talk. So let's be a little bit more formal. In a nutshell, the conventional way of extracting distributions of observables from single-shot images is these averaging formulas. So the experimentalists take many images and then they sort of stack them together and make an average, and they extract the sought distribution of the observable that they want, like for instance the probability to find particles at a certain position in space. They extract that via averaging many images, and this sort of goes the direction of all the fluctuations that you get in these single shot images, which are projective measurements of a many body state. All these fluctuations are averaged out. They are not used, they are averaged out, and the result of the averaging is then the sort of observable, which is displayed here. And yeah, it actually means that with averaging you fight quantum noise in your, or quantum fluctuations in your images, as opposed to what we want to do. We want to use these quantum fluctuations in order to get more information out of the same amount of images, or get different information out of the same images. And this is shown in this picture by just replacing this averaging step with a machine learning tool, and in our case this is a convolutional neural network. So yeah, maybe I should say, please, if there's anything unclear that I'm saying, just interrupt me and ask your question right away. Yeah, on the higher level, this slide gives us also repeats the outline of the talk. So first, I'm going to discuss about the input data which we generate by simulations, but equivalently they could be just images of ultracold atoms. Pictorially, these images are represented here, and we are going to feed this data into a machine learning algorithm in order to extract distributions of observables here, like the density in position space, momentum space, or the two-body density in position or momentum space. So that concludes the introduction. Let's come to the Hamiltonian and the data set, the theoretical background. We consider, for the sake of simplicity, state of a variable number of bosonic ultracold atoms in a double well potential. The double well potential is shown as a picture here, and to make our data set as diverse as possible, we randomize the parameters in the Hamiltonian, which we solve with the MCTDH-X software. So we randomize the height of the barrier, the width of the barrier, the tilt of the potential, the number of particles, and their interactions. And then in our data set, we have 1,000 single shot images per ground state that we simulate. We have in total 3,000 ground states in these randomized double well potentials. And of course, we compute the observables that we are going to try to predict with our machine learning tool, which is the one body and two body density matrix. But other things are possible, like the potential, which I guess Miriam has been introducing in her poster. So how do we solve this Hamiltonian? We solve it using the multi-configuration time-dependent hard tree for indistinguishable particles. So I won't go into much detail here, but technically solving this problem is too complicated if you have a sufficiently large number of particles, because the wave function that the state that you're going to get out is high dimensional objects, and you need too many numbers to represent that to even fit in memory. So MCTDH-X breaks down this high dimensional, computationally unmanageable object, the many-body wave function, into low dimensional, adaptive but computationally manageable objects and forms products which are weighted of these objects. We call them orbitals. And then the weights are these coefficients, and these products of orbitals, they form symmetrized spaces states. And then we just use the variational principle and derive some equations of motion, which are complicated, but we can solve them numerically. So, and this allows us to get a fairly accurate prediction on the true many-body state, and we can simulate also single-shot images from this state. I will discuss that later. The observables that we are going to deal with are the one-body density and its diagonal, the density. The one-body density is an expectation value of field operators, or alternatively can be written as a trace or in a basis. And its diagonal is just when we make the first argument identical to the second, we get the diagonal, the density. And similarly, we will also discuss a two-body density, which is a trace of a larger number of field operators. It can be written in position space representation like this, or in a basis. And the diagonal of the two-body reduced density matrix is the two-body density. So what are single-shot images? This is the last theoretical description for the observables. Single-shot images are the standard readout of ultracold atomic systems, and they correspond to drawing one random sample from the many-body state. So you can really, it's a simple probabilistic picture. You have a probability distribution, which is the many-body state absolute value squared, and you draw one sample of positions. We denote them here by S1 to Sn, which is the positions of all particles, or it can also be the momenta of all particles if we choose a momentum space representation here. And of course, if we have a correlated state of interacting particles, then these correlations are going to be embedded in our random samples S. And in this talk, we're going to try and use these correlations in order to get more information out of these pictures. So to give you a feeling of what these images look like for the subject of the present talk, okay, our double well potential, I chose one set of random parameters, which is shown above, like one number of particles, interaction, one barrier height, one barrier width, and one tilt, okay? And I just plot some single-shot images as well as their average. The average is this red line on top, and the single-shot images are the lines on the bottom. And you see, okay, when I skim through these slides, the positions of the particles in each detection fluctuate, okay, while the average, of course, the density stays the same, since we consider the same many-body state. And our task is sort of reconstructing the red line from the noisy lines on the bottom. Okay, so again, now we come to the machine learning introduction part. So we want to get observables via supervised regression on quantum measurements. So basically, we define a parameterized model of interconnected layers of artificial neurons, where we call this model F, and we want to predict some observable Y, which is obtained by feeding some data into our model, and we call the data X. So we want to find a model F of X which predicts y. Now, of course, with the usual process is we train this model, we adapt the parameters in the model in order to obtain an accurate prediction. And so in this talk, to be specific, we will use convolutional neural networks as our model F, and we want to infer physical observables, namely one-body and two-body density distributions from single-shot simulations X. So I'll run you through convolutional neural networks because, okay, I find it instructive. The typical way that this works is you have an input image, and then you apply a filter to all possible patches on the input, and you get an output image that has a different size. This is a convolution. And pictorially, this sort of works like this. I apply the filter on the first patch on the top left. I get by forming the convolutional product, I get this entry, and then I continue and get all the entries of the subsequent of my output image. And more formally, what we actually did by applying Unicorn is displayed here. So we stacked the single shot images of our ultracold atoms together to form an image. And then we applied like 3 different convolutional layers, and in between some pooling. For the details, I refer you to this preprint, which is hopefully going to be published soon. And as the output, we have the full distribution, like on the position space grid or the momentum space grid of the one-body or two-body densities, which is a number of grid points or the number of grid points squared. So in our simulations, this is 256 or 256 squared output variables, which is a large number compared to what people conventionally are doing, like classification tasks where you have a single output or maybe 2 or 3 outputs. Here we have a lot of output parameters. So let's come to the results. Can I get a quick update on how I am with time?
You're fine.
How much time remains?
I think you can have 5 to 10 more minutes. It's fine.
Okay, good. So I can show all the results. So as a first measure, so we use a number of single shot images in order to, in position space, this is important, so to extract the one-body density, which is the diagonal of the one-body density matrix. And we see, okay, so first of all, this top left panel shows the comparison of the predicted and the true values for our complete test set. So you see that the predicted and the true value are almost identical in pretty much all the cases. So this red line shows that the prediction and the true value is identical, and the blue dots in the histogram, they conglomerate nicely along this red line. Okay, and in comparison between the averaging approach and our machine learning based readout of this observable, the one body density matrix, we see that we gain roughly an order of magnitude, or sometimes even more, in accuracy when we use machine learning as opposed to the averaging approach. So the horizontal line, sorry, I cut the labels. The horizontal line in this graph is the number of single shot images that were used for the regression, and the axis extends from 0 to 200. So And this is striking news, okay, at least from my point of view, because we outperform conventional averaging, okay, by a factor of 10 when we use just 10 single shot images. So this means you can get way more accurate results reading out your experiment with ultracold atoms when you just, instead of fighting noise with averaging, use it with a machine learning tool. This is the nice news here. And on the bottom, okay,
can I have a question?
Of course.
So, thanks a lot. This is super interesting. So just to check that I follow your procedure correctly. So those errors you're basically, and accuracy you're showing on the data which you generated theoretically, right? I mean, from the calculation that you showed before, right? So you're comparing the true.
Yeah, but so we simulated. Yes, we simulated the measurements from our wave functions, and we also computed directly from our wave functions the density in this case. Yes.
Mm-hmm. And then in the experimental case, do they have a problem of having a finite optical resolution or something like that, which is usually common in ultracold atom experiments?
Yes. So there is, of course, a lot of problems with the imaging systems in on the experimental side. So they have finite resolution. They may miss detection of atoms. They may have noise, but there is examples, as I've shown in the introduction, where you actually get really single atom resolution with almost 100% fidelity.
So then you basically don't have to try to take into account for all this.
We did this. Actually, we did it in the supplemental information of our paper. You can find some examples. I would refer you to that. So we added artificial noise in order to test the predictions, and it's remarkably stable against noise, as you would expect for machine learning tools. They're good with noise.
Okay, good. Thanks a lot. Very well done. I mean, I like your work.
I will continue with the other results. Maybe so. I'll go a bit more quickly through those. So I was just about to mention. Yeah, I mean, of course, we have the obligatory comparisons of two examples here. So one comparison shows that shows a case where the density due to the tilt of the double well was located just in a single well, and it manages to predict that correctly. And the second example shows where the state is really delocalized between the two wells. And the results for the averaging were computed with this formula. So now let's increase the difficulty a little bit. We added results for the two-body density matrix, where the output is now 256 points squared distribution. So it's 65,516 or 36, I don't know, output variables. So it's quite a lot, okay? And still we get a similar behavior of this error. Of course, for the two-body density, the averaging formula is a bit different. And we see that, okay, our predictions nicely align with the true values as shown in this histogram. And this, of course, reflects also in the samples that we show here. So, okay, this is done. What can we do? What else can we do? We wanted to try something that you actually cannot do as easily in an experimental setup. So we tried to do a regression of the momentum space density, momentum space observables from real space single shot images. So these images are in real space, the input data, and thought observable is in momentum space now. And we see that it still works quite flawlessly. Okay, the true and predicted values align nicely, and our comparison with the averaging is still favorable with the machine learning. And here we should say that this is an unfair comparison. We chose the most unfair comparison possible. Namely, we took the momentum space single shots and averaged them. And yeah, because there's no way to compute, or no direct way to compute from the single shot images in real space via averaging the momentum space density. So we took the momentum space single shots for the averaging, and still we find a favorable efficiency when we use the machine learning way to read out these measurements. Okay, and also the comparisons check out. And so, okay, here's the same story for the two-body density in momentum space. And I guess, okay, I won't discuss the panels in detail. So you can see it's nicely establishing this way of picturing a quantum measurement as a supervised regression task, and it demonstrates that you can gain a lot in efficiency here. Of course, it's theoretical results, so we will have to still test this with true experimental data, but I'm confident that we will also have nice results there. So let me wrap up. Unicorn, the universal neural network interface for quantum observable readout from n-body wave functions, enables very accurate extraction of observables, and it allows real to momentum space inference. Okay, so we can use real space images to infer momentum space observables, or vice versa. And as a yeah, let's say an outlook or a to-do list, yeah, we want to further optimize the architecture of our networks using AutoML tools, where the let's say tedious loop of optimizing the architecture of the neural network to perform the task optimally is just automated. We want to consider other observables, namely high order correlations. We only went up to order 2 here, so there is many more. And we are looking for applications with experimental data. And yeah, with that, thanks for your attention. Here's some further info. I hope you have some further questions.
No, thank you very much for the nice talk. So are there some questions from the audience?
Yeah, can I bother you a bit more with questions?
Of course,
I'm very interested. So, of course, I'm interested in basically how you would how you would compose the arguments to basically this question. So, of course, your method basically depends on the assumption that the Hamiltonian that you take as an ansatz to describe the experiment exactly fits the experiment, right? Whereas in the experimental realization, we know that that's never exact. I mean, the system could, the true Hamiltonian describing the dynamics could be, something much more complicated, could have, imperfections. I mean, for many sources, like the potential doesn't have to be exactly like that. There could be atom losses that contribute, different boundary conditions and so on. So how would you, and then of course, since you take you train your model with the exact Hamiltonian that is describing your theoretical data, then of course you get a good result. But then if you want to use that on the experimental data, how would you somehow argue that, your result is kind of not an artifact of your assumption for the Hamiltonian form, right?
Okay, this was a large series of questions, but I'll try to give a consistent answer. So
yeah, it was just one question actually. I just described it in a long way, but yeah, it's just one question.
So I mean, we do basically simulate the whole experimental cycle in this work, in the data that was shown in this talk. This means we have a model, which is the Hamiltonian. We assume this Hamiltonian describes exactly the physical reality of the system.
Right. So that's I think it's the sort of
we solve this as accurate as possible, and okay, it's close to being exact. I cannot say it's exact because we're not able to check whether it's the exact solution, but I'm confident that it's fairly accurate, the solutions that we generated. Then from these solutions we simulated
the assumption that
you're questioning the assumption that the Hamiltonian is...
Yeah, the assumption that basically the Hamiltonian describes accurately the experiment, right? So that's I think it's a delicate point, right? And it has to be, investigated with the proper...
if you want to deploy this method, this machine learning tool, so this is the question. If you want to deploy this machine learning tool to an experiment, I would do it in collaboration with the experiment, use experimental data for the training of the neural network. So, I mean, this comes back to basically this slide. Yeah. So we would use experimental data for the training. So we get experimental pictures, we feed them, and then we get a neural network that is able to predict observables. Now, the observables, for this, we will need from the experiment a highly accurate measurement for a few realizations. Highly accurate means we need many single shot images in order to perform the conventional averaging and to obtain these observables with large accuracy, and use them as the labels for our supervised regression. This is one simple, let's say, brute force way to apply this to experimental data. You can, of course, do a combined approach where you do transfer learning, sort of. So you train on simulated data first, then you exchange the last layer of the neural network and retrain this last layer, the output layer of the neural network, on some experimental data that you have. Yes, so there's a lot of possibilities to go forward with experiment, but as a central aspect, you first need experimental data.
So, but yeah, sorry, maybe I'm already a bit long with the questions, but still, somehow from the conceptual.
Sorry, but I think it would be better that you continue this discussion.
Okay, yeah, sorry. Okay, thanks.
Are there other questions? We have time for one more question. So if no, let's thank Axel again for the nice talk.
Yeah, thanks for listening.
And now we will have like the